So we're starting unit. So we're starting unit 3, week 1, and we'll be talking about our first week, transducer resolution and artifacts. We mentioned in class that we are using a certain type of transducers. This is just showing the some of the different types that we have out there. We're using the phased array transducers, so we're going to be concentrating our information on this right here. You can also use a curved array probe. This would be more for general ultrasound, abdomen and abdominal scans and such, and a linear array probe, which would be more for probably more vascular type stuff. And just to review, I'm sure you guys learned about this in physics, but basically we depend on this, what they call the piezoelectric effect, which basically is the conversion of electrical pulses to mechanical vibrations and the return of those vibrations back into electrical energy. So a lot's done by the transducer, and in order to get our images, that's our major tool. So the piezoelectric effect is something that we utilize every second of every day when we're working, basically. And basically, as it says here, the ability of certain materials to generate an electric charge in response to applied mechanical stress. And essentially, this piezoelectric material will do that. We don't need to know too much about this, and don't worry about too much about this for test purposes. Just have an understanding that we're using something that has the ability to do this in order to generate an image from the human body. So our discussion is going to focus on mainly the transducer that we use, which is a phased array, and it's Philips, what they call a matrix transducer. We're going to talk a little bit about our resolution, both axial and lateral resolution, spatial contrast and temporal, and some artifacts that we run into when we're doing some scanning. And it says here a phased array transducer is usually composed of up to 28 individual elements in a smaller package than a linear array. And the reason that's smaller is because we have an area we have to see the heart and between the ribs and so on and so forth. So phased array transducers, as it says here, fire individual elements on the array in a specific sequence in order to direct the sound waves in a particular pattern. And this is best for echo because it has a very small footprint, which we've discussed in class, and it can still manage to see a large area. And if you watch a phased array transducer, essentially it's firing these elements in a row here. Bing, 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 bing. These are all coming down. So it can fire across and fire back this way. It's going to swing through the image such like that. And this is happening, of course, a million times per second. So we get a... The transducer we use is the Philips X51 matrix array, and I've told you a little bit about this, over 3,000 elements and such, but we're going to talk about this just a little bit for review. The features and ability of the X51, as I said, 3,000 plus elements. Philips has their own, each manufacturer has their own, what do you want to call it, terms for different things that they devise. And so these are proprietary in that nature, but they all basically have very similar capabilities from the different vendors. They just name it something else, and they come up with a different way of managing to improve an ultrasound image. But they all, think about it, physics is physics, so they all have to tackle this in some basically the same way, but they end up naming it their own their own things, so to speak, for their own terminology. So they've developed what they called something called pure wave technologies, term for the crystal properties in their transducer. These crystals, as you can imagine, had to be very finely cut because there's 3,000 plus crystals in their X51 transducer. And each transducer, this piezoelectric material has what they call dipoles, and when the machine is turned on, the transducers used, these dipoles are aligned when polarized. And you don't have to know a whole lot about that, but just understand there's a lot going on in there, and it creates this, as we know in the phased array, it creates this pie-shaped image, and as we said before, a very small face to help with fit between the ribs. And it's the most common type of for heart imaging simply because of its characteristics in that regard. Excuse me. So again, thousands of elements, many rows allow for electronic focus in both the azimuthal and elevation planes. Azimuthal is sort of a, how do you describe that, looking up and down, kind of directing out, if you will, and widening as it goes out. Electronic steering control throughout entire 3D field, as you can see over here. This is electronically steered and whatnot, sort of a cartoonish illustration here of our matrix array transducer. And when we turn on the 3D imaging, this kind of happens with the X51. It fans out all over the place, and it's going to get these the whole heart and generate the image that way there. A lot going on right here, as you can imagine, and this is the image we end up with. We're going to do this in class, and we're going to generate 3D images on each other, so we'll be able to know that when we go out in the field. It's a very easy process, and Philips has made this as easy as possible through what they call diagnostic heart model. And essentially that program, once you acquire your 3D data, take the image of the heart, you press a button and the machine will be demonstrating this in class again, and basically it just creates this 3D image of the person's heart. And how Philips does that is it's taken images of about 1,000 different hearts, so they tell us, and it best fits that heart shape to what's in the database and creates this image. And basically get a lot of information from this. We can get the size of the left ventricle, size of the left atrium. You can also do this on the right side too, but primarily we're talking about systolic function of the main pumping chamber. And all this information is available, the ejection fraction and so on and so forth. The other thing the X51 can do is it can, as I said, in the elevation plane. So it does this azimuthal plane and elevation plane, azimuth this way here, back and forth, up and down. So it's a really fancy tool, and just think about how much technology and R&D goes into the development of this transducer type. This is a transducer view image showing the X-plane capabilities of this transducer, and basically when you turn this on, you have X-plane, you have this plane here and this plane here. An X-plane can show two different, if you're looking at, for example, if you're looking at the aortic valve here, this is a transesophageal image, but basically just look at the aortic valve, looks sort of like our image there. When you turn X-plane on, it also looks at it from this angle here. So this angle and this angle, both en face, if you will, and from the side comes on simultaneously, so the doctor can observe these leaflets from both angles at the same time. It's pretty cool. I'll show you how that works. We also have something called an eye rotate feature. I don't use this too much, but this has been around for a while now. But we showed you that a little bit in class. We can just turn a knob, and if you get in, say, the 4-chamber view, you can turn the knob and go through to in 5-degree elements and get to where the apical 4 on the long axis is, and without even turning the transducer. So not a bad tool to use. They recommend we try to use this during stress echo, so you don't have to flip your hand so quickly to get the image. You just if you just hit the button, it'll automatically remember the degree as to which the next image is. The example is the 4-chamber view, and that's at a certain degree, and this is the 2-chamber view, and that's at a certain degree, and it actually is at a certain degree. To be honest with you, the 3-chamber view is set at a certain degree too. You set up those degrees, and you set you make a setting in the computer, and you save those settings in the machine rather. And then when you go to do your stress echo, all you have to do is hit the button, and it automatically changes to this and this one here, and you don't have to even move your hand. Now the problem is not everybody's heart sits exactly where it's supposed to anatomically set, and therefore you have to kind of set these up per individual if you want it to be completely accurate. And so I don't use this a whole lot, but supposedly it's a time-saving feature when you get to use your stress echoes. And I can kind of understand how that would be. You don't have to turn your wrist or anything, or hand or anything. Okay, what we want to concentrate on a little bit in this section here is on resolution. I know you guys are taking physics with Norma, so I'm assuming you've gone over probably most of this, but we're just going to I guess, emphasize from our perspective the importance of resolution, be it axial, lateral, temporal, contrast primarily is what we're talking about here, those different types of resolution. And just a reminder, if you guys have already had, I know you guys already had this in normal class, but anyway, axial resolution talks about being able to determine basically the separation of objects along a straight line down from the transducer, whereas lateral resolution looks at being able to determine where objects are in the lateral plane. Whoops, sorry about that, guys. In the lateral plane, if you will, and that's back and forth this way here. Axial's this way here, straight up and down. Lateral's back and forth. Then you have contrast resolution, be able to determine how clearly you can see an object and what have you, and temporal, where that object is in time. So temporal resolution is really important in cardiac because our heart is moving all the time. And therefore we got to see a moving objects, whereas as opposed to, if you're looking at a thyroid or the liver or a spleen or a pancreas or whatever, that object's not moving. And so temporal resolution really isn't affected in that regard, but for us it is, because the object is moving. We have to hit that with so many frames, pulses and whatnot, and bring it back to the transducer so that we can catch the movement of the object and how it's correctly moving, so to speak. So axial resolution is also known as spatial resolution. Again, axial resolution is up and down this way here. And that's, again, just to say the ability to resolve two structures that are parallel to the ultrasound beam, right? Jeez, I keep doing that. I'm sorry, guys. Parallel to the ultrasound beam. Also called longitudinal range, radial, or depth resolution. The frequency increase improves axial resolution, so a higher frequency transducer improves axial resolution. Directly related to pulse duration, therefore the shorter the pulse, the better the axial resolution. Just think about that. We got to be able to see between these two objects here. So a shorter pulse would allow the pulse to come down, go back, come down, and go back, and better define these objects that are, they're actually separate from each other. If this was a longer pulse, it would go down and perhaps not fit between these two objects, and therefore wouldn't be able to differentiate these as two different objects. Generally superior, to lateral resolution, although comparable in the focal zone of the transducer, and not affected by the image depth. And if you compare like a 5 and 10 megahertz transducer, you see doing the physics and whatnot, and basically the physics are that if the speed divided by the frequency will give you the wavelength, but in a 5 megahertz transducer, the wavelength is this. 10, the wavelength is this. If you do the same number of cycles, pulse length, approximately a millimeter is going to be exactly about half of that. In a 10 higher frequency transducer, maximum resolutions between two objects about 1, and the higher resolution transducer, the resolution is going to be about half of that. So you can see the difference between a 5 and a 10 in the axial resolution, and why a 10 megahertz transducer will be able to pick up the objects and separate those objects a little better. The problem is when you go up in frequency, of course, you lose depth with that because of the waves, just not attenuation and so on and so forth. So here's an axial resolution scan, and we can see that we have poor resolution here. These objects, our wavelength isn't high enough, or short enough. Pulse length isn't short enough. Our frequency isn't high enough to differentiate between these two objects here. However, if we switch to a higher resolution transducer, higher frequency, we can get better resolution right here. In the separation of these two objects, we can see these objects aren't one, but they are actually two. With lateral resolution, or azimuthal resolution, remember that's in the plane here, azimuthal plane, elevation plane, azimuthal plane. That's the ability to resolve closely spaced perpendicular structures, right? also called angular, transverse, or azimuthal. So within perpendicular structures to beam this way here. So the beam is sweeping through here, and the ability to resolve these this way here. The reason this isn't as good in many situations is because first off, it's here you're going straight down, and as you spread out the beam, the resolution, it loses its not as many well, excuse me, you make it wider and whatnot. It's got to sweep through this area, so this resolution is going to be a little bit wider than this here, and you're not going to be able to see things quite as well simply because of that. Equal to the sound beam width, right? So if the sound beam width is really wide in that area, it's going to be difficult to see these two objects really clearly. Increase the transducer diameter, increase frequency, and or focus. And so if you increase, it sounds kind of counterintuitive, if you increase the diameter of the transducer, increase frequency and or focus, and that'll improve our lateral resolution. And if we increase the diameter of this transducer, the beam's going to be able to focus down more narrowly in the focus zone. We'll talk a little bit more about that later on. And it is affected by depth. Width changes generally not as good as axial resolution, less in the focal zone. So depth affects is the width, and therefore the further down we go, the wider this beam becomes, the poorer our resolution becomes in this area because of the spreading of the beam. A bit more information to try to, more scan lines to try to produce, and it just can't separate these two objects as well. Here you show axial resolution up and down, lateral resolution this way and this way. So in order to get good lateral resolution from a probe, we could have scan lines that come down and separate these two things and come back and let us know that these are two separate objects. Boom, 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 boom. It just goes boom, boom, boom. It thinks these objects are just one. Probably a poor explanation, but I think you kind of get the idea. So we've done axial, we've done lateral. This is just a quick review. As I said, you guys have all had physics. So contrast, let's talk about contrast resolution, the ability of an ultrasound system to demonstrate differentiation between tissues having different characteristics. For example, the liver and the spleen. Believe it or not, they do look different with ultrasound. And people who read these, which would be radiologists, they do know the difference between those textures, if you will. The ability of grayscale to distinguish between echoes of slightly different intensities is what contrast resolution is. It depends on bits per pixel, the dynamic range or compression. It's a post-processing process and it ends up on the display, improved by increasing bits per pixel number, changing compression, or changing contrast brightness settings on the display monitor. We're going to talk in class about how to do that. Remind me to tell you how we change the contrast on the brightness settings on the display monitor. But right here is a contrast resolution. Poor contrast resolution, I should say. This is the heart, right? You can see the kind of the outline of it. And this is probably due to compression settings or a grayscale setting, but just poor contrast resolution. We don't see really any of the endocardium here. We see the outline structure of the heart, the septum here, anterior septum, and the infralateral wall here a little bit. See maybe a little bit of the endocardium. We have to see the endocardium, which is this right here. So if we change our contrast resolution through grayscale, compression, or whatever, we can see we get much better contrast resolution here. And perhaps we changed our probe. Maybe went to a res setting instead of a pen setting or something like that. But this is considered good contrast resolution in comparison to that. Okay, this is too bistable, if you will. It's just too black and white. You need more grays in there to see this. That's what contrast resolution really talks about. And here you can see the same thing where you have more detail in this here versus this one. He has a little less. That's a brain, by the way. And once again, the liver and spleen, I know we don't do general ultrasound, but you can see the liver's, the contrast in the liver looks a little bit, whoops, sorry guys, looks a little bit different than what the spleen is. Okay, and this is the kidney, even a little bit different than that. So if we have good contrast resolution, the radiologist who's reading these can see the difference in the texture of the organ. So that's all we're going to talk about is that's how we're going to just highlight those resolution, different types of resolution. Okay, and let's move on to temporal resolution, which is really affects the frame rate and therefore affects hertz or frames per second, basically. So the human eye is only capable of recording and interpreting frame rates of about, so if you look in the literature, about 45 hertz. But the better, the more the better, right? We can go above that, but we want to try to stay above a certain range so that we can see the movement of the heart, especially affected by temporal resolution. The basis of temporal resolution is our formula, if you will, where F equals frame rate, C is the speed of sound, D is the sampling depth. It's affected by depth. We get 2 times the depth. Number of sampling lines per frame would be here, and we get number of focal zones used to produce an image, and that typically, I don't know how many focal zones we can use. I think we can narrow or change the width of our focal zone, but I'm not sure if we use more than one focal zone. I think we only use one focal zone in echo on this transducer we're using, so I wouldn't worry too much about that. But that's the formula. You don't have to know this formula. That's basically what the machine is calculating for its algorithm. So temporal resolution is the time from the beginning of one frame to the next, which basically means frame rate. The number of ultrasound images displayed in one, not sex, I'm sorry, that should be said, and is expressed in hertz. How the heck can I put that in there? The ability of the ultrasound system to distinguish between instantaneous events of rapidly moving structures during the cardiac cycle. So it's all frame rate dependent. So basically temporal resolution, if you think of temporal resolution, think of frame rate and therefore think of hertz. Per second is what hertz means. So for cardiac imaging, if you talk to most people out there, we want to keep our frame rate 18 hertz and up. Seems to be that's where most people, you don't see a jumpy image, so to speak. You see something that's smoothly moving as one image. Everything's, it's not jumping around on the screen on you or something like that. So the higher frame rates maximize temporal resolution or maximize frame rate, obviously. And we can increase our frame rate by keeping our depth as shallow as possible, decreasing our sector size, our box size, because that's going to increase our scan lines, and therefore increase our frame rate. Decrease our focal zone, make sure we put our focal zone where we are actually scanning at. A lot of people forget about that focal zone. And again, reduce the number of scan lines. And we have a function on our machine. I'm going to talk about this in class. It's called the res speed function. And that there will, I'll show you how you use that. And that definitely helps with temporal resolution by changing the number of scan lines, where if you move towards this, more scan lines. If you move towards this side, less scan lines. So again, improve with decreasing image depth, decreasing image field of view, and decreasing line density. Remember, if you decrease line density, you decreased resolution too. So there's a give and take here. And this is just showing us, as we fan out the number of scan lines, the wider our depth is and the deeper our distance is. See how the scan lines go out a little, separate a little further. So if you reduce depth of scanning, sector width unchanged, let's see here, temporal can improve by fewer scan lines here. See, the scan lines are further apart, so that's going to similar. I want to say, I can't even read this thing, but basically know that it's affected by the number of scan lines, the width of our scanning field, as we said, and image depth. Okay, don't worry too much about this image here because I can't even read the daggone thing, but perhaps you can see it better than me. So key points on resolution, and we're talking about key points on all of our resolution. We're almost done here. Key points on our axial, lateral, temporal, and contrast resolution. And again, this is just a quick overview because you guys have had physics, so we're just kind of touching upon the highlights here. With axial resolution, that improves with increasing frequency due to shorter wavelength and pulse, being able to separate two objects in a straight line from the transducer, basically. Lateral, to improve that, improves with increasing the frequency due to beam near field length. Narrow beam width increases lateral resolution, increasing the focus length again. Temporal resolution, moving structure seen accurately. The heart's moving all the time, so we need to have good temporal resolution with the heart. Very frame rate dependent, improves by decrease in depth, width, and line density, our res speed function. In contrast, resolution, grayscale number, more grayscales, a better detail. That's adjusted by the compression dynamic range on our machine and also our monitor brightness, perhaps. Okay. So let's just talk a little bit about artifacts. I'm not going to spend much time on that, but types and tips to reduce artifacts types that we see in ultrasound: shadowing, near field, reverberation, mirror imaging, side lobe artifacts, beam width artifacts. And we're not going to go into too much depth here. We'll be talking more about that in Echo 2, probably a little bit more. But just so we know that we do run into these things, and just quickly what they're about. Shadowing, very common artifact, sort of known as the quote-unquote Achilles heel of echo, happens when the beam encounters a medium, in other words, a structure of significantly different acoustic impedance, and as a result is reflected back to our transducer. And that happens in, this is a transesophageal image of a, right in here, this is the left atrium and this is the left ventricle. And the transesophageal image, that's always first in the picture. And what we have here is a mitral valve replacement of some sort. Looks like a mechanical mitral valve. We see the stents here, our beams coming in. And what's happened is we can't, you see this shadowing artifact over here. Again, we're talking about shadowing and attenuation. So we can't see anything over here. What's happening, this beam is our pulse is coming down, just hitting this metal structure, and all of our energy is just being reflected back. So we get very, very little penetration. And so we can't really see down in here into the left ventricle. It's just being wiped out by this attenuation, if you will. Here in general ultrasound, this is a kidney right here. That's what a kidney looks like. And if you see a stone in the kidney, which is that is, you can see after that stone, you can't see anything because the ultrasound beam's just hitting that. And it can't penetrate that, so we don't get anything beyond it. You just get this shadow line down in. So that's an example of a shadow artifact. What happens to us a lot in echo is something called a near field clutter artifact, or something referred to as rain down. And that's caused by high amplitude oscillations of the piezoelectric crystals of the transducer itself. Harmonics has helped this, but we still see this and may mimic a possible apical thrombus. And here's what's called ring down artifact. This is a two-chamber view, if you can appreciate that, left ventricle, left atrium. And this mess up in here, in the apex, if somebody gets a clot, typically it's going to end up in the apex. So that's the lower portion of the heart. And everything kind of sticks down in there. Just gravity kind of takes over there. But see all this mess down in here? That's actually not a clot. That's the oscillations back and forth between our transducers right here. And it's hitting this bright surface of the heart here, the epicardium or pericardial sac and whatnot, but arises from high amplitude oscillations back at the energy bouncing back and forth. The artifact is troublesome when trying to fire structures that are particularly close to the transducer, and it has been reduced in modern day systems with harmonics, but this can happen, and we have to make sure we can differentiate between this and an actual clot in the heart. And that's called ring down artifact or near field clutter. So the ultrasound gets trapped and just bounces back and forth, as I said. Between two strong parallel reflectors. The wave reflects back and forth between, it reverberates. The ultrasound waves returning transducer are interpreted as deeper than they arrive, deeper structures since they arrive at the transducer at a later time. So it's a time artifact. Here's a reverberation artifact right here. Near field clutter, rain down, sort of a reverb itself. But definitely reverb artifacts involve this right here. And here's an example of a reverb artifact. Again, transesophageal image, I know, mechanical mitral valve sitting in this is the left atrium, this is the left ventricle. And when we hit this thing, it's going to vibrate between these two very strong structures, and it's going to just make this ring, sort of like this, not ring, excuse me, but these ladder effect. The ultrasound is going to just keep bouncing between these things. And you notice these are all equidistant. It's going to hit this, boom, back, boom, 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 and then return to the transducer. The transducer is going to think this is way down in here because of a speed difference, but anyway, see all these, this is all artifact reverberations due to this mechanical mitral valve. Here's another reverb artifact. This is actually a uterus, okay, and the IUD in the uterus. These are very bright objects. You can see this uterus. This IUD is not 1, 2, 3, 4, 5, so on and so forth. This is the uterus, the IUD right here sits in the uterus, and these are all equally spaced structures due to reverberation of this brightly solid structure right here. It's going to vibrate back and forth between the structure and the transducer to create these reverbs. This is something called a mirror image artifact, and that right there involves looking at the liver. This is the liver. This would be the gallbladder. And you see this right here. This is the diaphragm. Very highly reflective surface. And what happens, the ultrasound beam comes down, hits it, bounces back, and it produces this image that is a mirror image of the liver back over here. This isn't, the person doesn't have two livers. It's because of the effects of the, it reflects back later around the curve. See the machine's going to travel down, hit this, it's going to curve around this way here, and it's going to make this image down here. You don't have to know how this happens, but just know what it looks like. This is a mirror image artifact of the liver right there. We also have something called side lobe artifacts. These usually occur at strong reflectors outside the central beam, which is the side lobe. Low intensity beams surrounding the central beam is what side lobes are. The echoes are displayed as if originating in the central beam and may cause some sort of edge artifact, so the structure may appear wider than actual due to these side lobe artifacts. And if you look at the transducer here, you can see we have a focal zone. This is where our beam is going, our main beam. This is where we see things the best. Then it sort of spreads out here, and this is where our lateral resolution would be challenged, where lateral resolution would be here, and also our axial resolution would be here. Axial resolution would be better out here than lateral resolution due to the scan lines separating so much. But these are the side lobes that the ultrasound generates. It's just, power that's coming out here, ultrasound's coming out of here, and you want to try to keep it as focused as much as possible. And you can do that with a larger lens, and perhaps even a concave lens you can really focus this beam down, narrow it out. But we do end up with these side lobes and these grading lobes, and these can if this is being sent out this way here, the sound, not just this way, but this way, this way, this way, and this way, when pulses are emitted, it's going to pick up stuff on these in these areas too, and it's going to return to the transducer, and it's going to return differently, not right back and forth. So the transducer is going to end up with some weird artifacts. In this case here, if you see, this is our long axis view, parasternal long axis view. And we can see some stuff. If you look real closely, we see some sort of, looks like it may be something in the left atrium. This is the mitral valve. And you get this sort of a hypoechoic structure right here. And also right here, the strong echoes produced by the posterior mitral annulus, which is right, oops, sorry guys, keep doing that, damn it. Which is right in this area here, posterior mitral annulus. And atrioventricular groove produce a side lobe artifact that appears as a mass within the left atrium. Okay, that's really not a mass within the left atrium. It's a side lobe artifact. And if we look at that, how we know that, if we look at that left atrium from a 4-chamber view or a 2-chamber view, that won't be there, because it won't be the beams coming down, it won't hit this and produce, this artifact won't be coming from this anymore. It will be at a different angle. That's how we avoid these things, or try to. We have something called beam width artifact, where the beam comes down, straight down. It's supposed to come down in the focal zone, right? Then it spreads out. You can see where we're supposed to see this object here. The gray dot is assumed to be in the main beam area of interest outside the focal zone. Adjust the focal zone. Gray dot outside beam. See, it's outside now. Area of interest inside the focal zone. So even though we're trying to stay in here, this dot is showing up. We're trying to see this here, and we don't want to see that dot. So we're trying to get rid of it, so we adjust our focus by getting rid of that dot. That would be something called beam width artifacts, side lobes, so on and so forth. When do artifacts happen? Well, they happen with good image quality, because we get really good image quality, and we have a very good reflector. We'll have a mirror image artifact. They happen with poor image quality. They happen with strong reflectors, calcifications, mechanical valves, and so on and so forth. More frequent with fundamental imaging. Yeah, that means not harmonic imaging. So to minimize running into artifacts, we got to know our pitfalls, know the anatomy, be cautious of strong reflectors, and this is most important, use multiple views. And therefore, if we see it like I demonstrated here, if you see an artifact in the left atrium here, and is that an artifact? Is that a clot or something? If we go to the 4-chamber view, this won't be there anymore. So we got to be suspicious of that being, if that's not, it should show up in the other views. It most likely will show up in that view if it's truly a clot. So we know, we use these, know the pitfalls, know our anatomy, be cautious of strong reflectors, use multiple views. Here's a reverberation artifact. that's unfortunately caused a lot of problems. This actually came out of a journal. I think it was the journal, whatever the cardiologist used, Jack, I think it's called, Journal of American Cardiology. And this is a reverb artifact. This is an ascending aorta. This is an image of the ascending aorta. And look at this artifact right here. And what do people think this is a reverberation artifact? Once again, hitting a strong reflector, bouncing off, coming back. So what happens is the machine comes down, hits this, comes back, it bounces off, comes back down, hits that, and it thinks this right here is right here. So see how this is equidistant from this? See how this is the same distance? So that right there is very suspicious. And what this can be mistakenly thought of is a aortic dissection. And if you read in the journal Jack, I can't remember what the year it was, but this right here, a person actually got operated on thinking they had an aortic dissection, and it was nothing more than a reverberation artifact. So that's important to know the difference between aortic dissection and artifact. Again, the other thing that we can do, as we said, know the pitfalls, know our identity, be cautious, use multiple views, turn the gain down, adjust the gain properly, alter the probe angle, and watch the effect on quote unquote the artifact. Scan in more than one plane, try moving the patient, and perhaps even change the frequency. Okay? So that's it for this unit 1. I know it's a lot of information. We'll discuss more of it in class, obviously. But please review this before you come to class. Okay?